Hello everyone. In this video, we're going to break down exactly what a differential equation is and how to solve your first one. Let's jump right in. So, the word differential equation might seem scary if we haven't seen it before, but what does it really mean? Well, it's not that different from math we've seen before. Let's look at a simple algebra problem. If I were to try to solve the problem 2x plus 5 equals 15, how would I do this? Well, my goal is to solve for the single variable x. So I'd subtract 5 from both sides. I'd get 2x equals 10, divide both sides by 2, and ultimately end up at my answer, x equals 5, which is just the solution to a single variable. Now, solving for a differential equation isn't much different from that. The only difference is we're not looking for a single number. We would instead be looking for an unknown function that satisfies a condition posed by the differential equation. Now let's take a look at what that really means. Let's say I had the differential equation dy over dt is equal to 3y. At first, this might seem intimidating, but let's break down what this really means. The left side is just our standard calculus notation. It's telling us that the derivative of the function y with respect to the variable t, also known as the rate of change of the function y with respect to the variable t, is equal to some value. The right side is simply telling us what this value is, and in this case, it's 3y. What this really is saying, though, as a differential equation, it's saying that there is a function that exists that has a derivative which is equal to 3 times the function itself. So in the case of solving the differential equation, instead of solving for a single variable, we would instead be solving for a single function that satisfies this condition that it has a derivative that is equal to 3 times itself. So all this is really saying is that the derivative d dt of our desired function y of t that we're going to solve for has to equal 3 times the function itself, y of t. So that's an example of a simple differential equation. But why would we want to use these in the real world? Well, let's say we were working in a lab or a factory and we were trying to keep tracks of rates of change. Let's say, we were trying to see the concentration of a drug over time or how fast a patient metabolizes a drug. We would use differential equations to link that changing amount of the drug or the concentration and link it to its rate of change. And these will be very important in science and engineering throughout the rest of your academic career. However, before we move on to learning how to solve differential equations, there are some important terms we need to cover because they're going to show up repeatedly in your journey of learning how to solve differential equations. Let's start with the term ordinary differential equation, also known as an ODE. Now, this is a term that's going to show up in almost every course or problem you solve of differential equations. Ordinary differential equation just means that it's an equation that involves an independent x variable, a dependent y of x function, and the derivatives of that function, y prime, y double prime, or even y triple prime. Now, the equation doesn't need to involve all three of these things, but it involves some sort of combination of them, and that's what makes it an ordinary differential equation. Let's see some examples of this. So we could have the function the differential equation y prime equals y. That would be an ordinary differential equation. Why is that? Well, it's because it has the derivative y prime and it also has the dependent y of x function. Now, in this case, we didn't have an independent x variable, but again, we don't need to have all three of the components I mentioned earlier for it to be an ordinary differential equation. Because, for example, imagine we could just have the coefficient be 0, but the x term is technically still there. So that's an ordinary differential equation. We could also have something a little more complicated like y double prime plus y prime plus y equals 0. Again, it's using a combination of the derivatives of the function and the function itself and combining those into one differential equation. And that's something we could solve as an ODE. And finally, we could also include the independent x variable that I mentioned earlier. So we could have an ODE that looks something like this: xy prime plus y equals cosine of x. Now, all three of these would be examples of perfectly acceptable ordinary differential equations. On to the next term, a general solution. Well, first, let's think back to our Calculus 1 and Calculus 2 days. When we were solving indefinite integrals that didn't have bounds on each end of the integral, what did we have to do? Unfortunately, we had to add a plus c term to signify that this wasn't a definite integral and this was just a general solution to that integral. Unfortunately, a similar kind of idea comes back to haunt us in differential equations. A general solution to a differential equation is just a function that represents all possible solutions to that differential equation. But there was no initial value or like condition specified for that differential equation we just solved. So we have to put some sort of plus c or just c term in general to signify that this is just a general solution. So it's all possible solutions and it uses constants like c. So we could have a solution like y equals c times e to the x. That would be a general solution. We could even get something like y equals 3x plus c. That would be a general solution. So if you're seeing a c term or a plus c term, that means it's a general solution and it is not confined to a specific differential equation with a specific initial condition. Now, a particular solution is the exact opposite of this. Instead of finding a general solution to a differential equation that could go through many points on a graph, instead we're finding an exact function y of x that satisfies an ODE that has a specific requirement on it. Let's see what that means. Let's say we had the differential equation dy over dx is equal to 2x. Now we could go ahead and solve this in the normal way and find a general solution with a c term in it. However, let's say this problem specified the initial value or the required condition that y of 2 was equal to 10. Now what does this really mean? It means we're trying to find, first of all, a solution in a differential equation where the derivative is equal to 2 times the x term. However, at the same time, we're putting this condition that the solution has to go through this point 2, 10 on the xy graph. So that's something to keep in mind as you move forward with differential equations, recognizing whether the problem is asking for a general solution or a particular solution, and if there's a specified condition that they want you to satisfy with your solution to the differential equation. Now, these last two terms are not used as much, but they are very important to understand. So the order of a differential equation is the highest order of derivative we see in the differential equation we're looking at. Now, what does this mean? Let's look at an example. Let's say I had the differential equation y double prime plus y prime plus y equals 0. What would the order of this differential equation be? Well, if we remember, the order is just the highest order of derivative we see in the differential equation. And we see here that we have a second derivative term, and that's higher than the first derivative term and the no derivative term. That would mean that the order of this would be second order because that's the highest derivative term that we see. Now let's look at another example. Let's say we had y prime equals y to the fourth power. Now I want you guys to think about this one because this is kind of a trick. What's the order of this differential equation? Well, if we look at it, remember, the order is just about the highest order of derivative we see, not the highest power we see. So you might be tempted to think that this is a fourth order differential equation. However, this is not a derivative term. This is just an exponential term. It's y raised to the fourth power. The only derivative term we actually have in this function is this first derivative term right here. So this is actually a first order differential equation because the highest order of derivative we see is a first derivative. Now, our final term is linear differential equation. Now, what does this mean? This just means that we don't have powers on any of the y y prime or y double prime terms. What does that mean? Let's look at some examples. Well, the previous example we already looked at, y prime equals y to the fourth. Let's think, would this be linear or would it not be linear? Well, we just can't have powers on any of the y-related terms, so any y variable or its derivatives. Unfortunately, here we see that the y on the right side is raised to the fourth power, so this would not be linear. Let's look at another example. Let's say we had y prime plus y double prime plus y equals 0. This would be linear because none of these derivative terms are raised to any power. It's not y double prime to the second power, y prime to the third power, anything like that. It's just y double prime plus y equals 0. So it's a perfectly linear differential equation. Now for our final example, let's look at this. Xy prime plus y equals cosine x. Now I want you to take a moment and really think about this one. Is this one linear? Well, we might think that because the y prime is multiplied by x on the left side, that this isn't linear anymore. However, the actual power on the y term is still 1. It's not y to y prime raised to the second power or third power. Just because it's multiplied by an x doesn't change anything about its power. So because the y terms in this differential equation right here don't have any powers on them, this is still linear. All right, so now enough chatter about terms and definitions and all that. Let's solve our first ODE. So let's say we had the differential equation y prime equals x, and we were asked to solve this. Now what would we do? Well, looking at it like this, it looks a little confusing. What is y prime? How are we supposed to break that down? So something I personally like to do is rewrite this. We know from calculus that y prime is the same as dy over dx equals x. The next thing we would do is kind of like our instincts tell us to do in algebra. We would want to get all the variables that match on the same side. So to do this, we see we have an x on the right side and we have a dx in the denominator on the left side. We could multiply both sides by dx and we would arrive at dy equals x dx. Now, what would we do from here? Well, it might not seem obvious, but dy is really the same as 1 times dy, and the right side is x dx. Now, using our skills from Calculus 1 and Calculus 2, we could just take the integral of both sides with respect to their respective variables. So if we took the integral of the left side, that would be taking the integral of 1 dy, which the integral of 1 is just the variable, so the left side would become y. And the integral of x, using the n plus 1 rule, would just be 1/2 times x squared. And there you have it. That's our solution to our first ever differential equation. However, because this did not specify any particular value or condition that we had to satisfy, we know that this is supposed to be a general solution, as I previously mentioned, and this isn't a particular solution to any specific differential equation. So we're going to have to remember to add a plus c variable, and that's our final solution. Now, this skill of verifying the solutions to differential equations is going to become really important when we get to solve more complicated differential equations later on in our journey of learning how to solve differential equations. We might not always know how to solve something, but for now, we need to know how to at least verify that the solutions we are given to a differential equation that we can't solve with the methods we know is indeed true. So let's try it out. Let's practice it. Let's say we're given the differential equation y double prime plus 9y is equal to 0. And, looking at this seems kind of complicated. We're not really sure how to solve this yet with what we know, but we are given two functions that, whether it's an exam or just a homework problem, the problem is claiming that these two functions should satisfy the differential equation. So we have y1 equals cosine of 3t, and y2 is equal to sine of 3t. Now, how do we go about verifying this? Kind of like how we did with the previous one with the solving for y equals y prime, and we found that it was e to the x by plugging it in. So we will pick one of these functions. Let's start with y1 and see if it's actually going to satisfy this differential equation, y double prime plus 9y equals 0. So let's go ahead and work our way to finding the second derivative of y1. So the first derivative of y1, we got to remember to use the chain rule. We know that the derivative of cosine is negative sine, and we know that the derivative of 3t is 3. So we know it's going to be negative 3 times sine of 3t. We take the derivative again of y1 double prime, same idea. We know the derivative of sine is cosine. We know the derivative of 3t is 3. And using the chain rule, we know this is going to be equal to negative 9 cosine 3t. So we're going to keep our eye on this and plug it in later. For now, oh, never mind, because we don't actually have anything else to solve for. So we've solved for y double prime, and we know that our original equation is y double prime plus 9y equals 0. So we're going to go ahead and plug this in. So we have negative 9 cosine of 3t plus 9y. So we're going to multiply our y term, our y1 term, by 9. So 9 times cosine of 3t should be equal to 0. Now let's see if this is true. Well, negative 9 cosine of 3t plus 9 cosine of 3t is basically the same as negative 9 plus 9, because the cosine of 3t is just the same thing for both. So negative 9 plus 9 we know is 0, so this becomes 0 equals 0. And yes, this is true. So we know for sure that y1 is a solution in this differential equation. We've verified it, we've plugged it in, and we know that yes, it verifies this differential equation. Now, we got to also test y2 as a solution in this differential equation. So we're going to repeat the same process. We always look at what the highest term or what the order of the differential equation is, and see what how far ahead of a derivative we need to solve for. So it's second order. Remember, flashback from the first part of the video, because it's the second derivative is the highest term we see in the equation. So we need to do the same thing we did with y1. And of course, we should have checked that at the start of the problem, but it's just always good to remember the concepts and definitions we discussed at the start of the video. So the derivative of y2 is, using the chain rule again, we know the derivative of sine is cosine, and the derivative of 3t is 3. So 3 times cosine 3t is our first derivative. And then our second derivative of y2 is, using the chain rule again, derivative of cosine is negative sine, and we know the derivative of 3t is 3. So this becomes negative 9 sine 3t. Now, if we plug this back into our original equation of y double prime plus 9y equals 0, we're going to get negative 9 sine 3t plus 9 times our original y2 term up here. So 9 times sine 3t has to be equal to 0. Now let's check if this is true. Well, sine 3t's, both those terms are going to cancel out. It's negative 9 plus 9 again, which we know is 0, is equal to 0. And again, this is true. So we've verified successfully that both of these satisfy the differential equation. And this is a skill that you're going to be asked to do maybe on your first, your earlier midterms or tests in class, but it is definitely a skill that will be crucial towards even going on and solving the next parts of a differential equation later on when we learn more complicated differential equations. So the last type of differential equation problem we need to learn how to do to have truly covered a true intro to differential equations is an initial value problem, which is also sometimes called an IVP. So let's remember what we talked about at the start of the video. We know that there are two types of solutions to a differential equation. We have a general solution and we have an exact solution. We remember that the general solution has a c term in it, or a plus c term, and it can be used to satisfy the solution to a differential equation that doesn't have a specified condition that needs to be true. We know, however, for an exact solution, there is no c term, and instead the differential equation is particular and satisfies a condition that was specified and requested by the problem. So an initial value problem is going to ask us to satisfy a condition that is true at the starting point of the problem. And of course, there are word problems and real world applications for this. Like, let's say we're modeling the growth of the population of a town, and we have the initial condition that at time t equals 0 years, the population of the town is 100 people. And our solution to that differential equation has to satisfy that. But for now, let's look at an example that's much simpler and looks at numbers only. So let's say we had the differential equation y prime is equal to 2y. This could be solved and we could get a general solution. However, we have the condition that y prime equals 2y such that the initial condition y of 0 is equal to 5 is true. So how do we solve this? So generally, we would find the general solution of the differential equation first, and then we would go back and plug in the initial value to solve for what the specific c term is in this case. To fast forward this process and just to get the grasp of the idea, we are going to be given the fact that we know that y is equal to c times e to the 2x. And we are given that this should be a solution, a general solution that satisfies this differential equation. Now, just as we just practiced, let's try verifying this and making sure it's true before we go on. So let's take the derivative of this y equals c times e to the 2x. So y prime of this, using the chain rule, we know that the derivative of e to the 2x, well, we know the derivative of e to the x is just itself, but using the 2x term, we know we got to multiply by 2. So the derivative ends up being 2 times c to the e, 2 times c times e to the 2x. Yep. Okay. So now plugging that back into our initial given differential equation, we write for y prime, we write 2c times e to the 2x is equal to 2 times c e to the 2x. And what is this really saying? It's just saying 2c times e to the 2x is equal to 2c times e to the 2x. So yeah, we know for sure that this is true. Awesome. Now let's move on to the next part of solving an initial value problem. So we know that y equals c e to the 2x is a solution to this differential equation. We've gone ahead and verified it and we know it's true. But it's just a general solution because we have a c term. We now have to plug in the initial value we're given and find out what this c should be. So we're given y of 0 is equal to 5. So we're going to plug in these conditions to their respective parts of the solution that we found. So when y equals 0, the left side y is just going to be 0. This is going to be equal to c times e to the 2x. And in this case, we know that x is 0. So 0 equals c times e to the 2 times 0. Now 2 times 0 is 0, and we know it's going to be e to the 0, and anything raised to the 0 is just 1. So we get 0. Oh, sorry, I made a mistake. Should not be 0 on the left side because y when x is 0 is equal to 5. Apologies for that mistake. So it's 5 equals c times e to the 2 times 0. So we get that 5 is equal to c times 1 because e to the 0 is just 1. And 5 equals c times 1 is just saying that c equals 5. Awesome. So now we're going to plug in this c value we found into the solution that we know is true and have verified for our differential equation. So coming over here, we're going to plug that in. We know that the solution to this initial value problem is y equals 5 times e to the 2x. And we know that this satisfies both the general solution to our differential equation and the fact that it has to satisfy the initial condition that at the x value equals 0, the y value is equal to 5. All right, so with everything we've learned in this video, I know it might be a lot, but take your time and try and go through these practice problems on your own. Feel free to pause the video, and when you come back, I will walk through how to solve each of these problems step by step. All right, so for problem number 1, we have the differential equation dy dx equals 2x. Now this one should be pretty simple. Remember, just like our instincts tell us in algebra, we kind of want to get each variable isolated on its own side. So let's start with that. If we multiply both sides by dx, we're going to get dy is equal to 2x dx. Then, if we integrate both sides, we get, because we know that dy is the same as 1 times dy, we get the left side is equal to y, and we get that the right side is equal to x squared. However, because we remembered there was no particular solution right here given to us, sorry, not particular solution, but initial value or condition, we know that this is a general solution. So we got to add a c. So the final answer becomes y equals x squared plus c. Now, we can also just do some quick mental math in our heads to check that this is really true. We know that the differential equation is really just telling us that the derivative of y is equal to 2x. So if we take y prime here, we would get that y prime, taking the derivative of the right side, is just equal to 2x because the derivative of x squared is 2x, plus c, well, the derivative of a constant is 0, so we get y prime equals 2x. And this is the exact same as this problem we're given right here. So we know for sure that we solved this right. And that's the nice thing about differential equations, is you can always plug back in and take the derivative and see if you really solved it right. Now, for the second one, this one looks a little bit more complicated, but I think we can still do it quite fine. We've got dy over dx equals x over y. Same idea, we're going to want to get each variable on its own side so we can integrate. So if we cross multiply here, we get y times dy is equal to x times dx. We now have each of the variables on their own side, and we can integrate with ease. So put the integral signs on both sides, integrate y dy and integrate x dx. We know from our calculus 1 and 2 skills that the integral of y dy is equal to 1/2 y squared, and the derivative of the right side, sorry, not the derivative, the integral of the right side is equal to 1/2 x squared. Of course, because there's no particular or initial condition given to us, we know that this can't just be left like this. We're going to have to add a plus c variable to show that this differential equation could validate multiple differential equations with different initial conditions, and we would solve for c if we were to be given one. And we can simplify this a bit, multiply both sides by 2. We're going to get y squared is equal to x squared plus 2c. Now, something that a lot of professors prefer and something I like to do is if I'm going to multiply my c by anything, instead of writing 2c, I would write that c1 is equal to 2c on the side. And then instead of writing plus 2c, I've already noted that on the side, so my professor, whoever's grading my exam, knows. And I'm going to write y squared equals x squared plus c1. That way I can keep the c as a c, because multiplying a constant by another constant, it's still a constant. So I like to represent it as a constant, just c. So it could be c1, c2, depends how many times I multiply the constant by the constant. However, of course, if we're going to multiply both sides by x for some reason, I wouldn't be able to do that because c times x is a constant times a variable. So you wouldn't be able to write c1 equals x times c. That wouldn't be allowed. You would have to represent it as x times c. Anyways, moving on. So from here, we can take the square root of both sides, and we get y is equal to plus or minus the square root of x squared plus c1. Awesome. Now, for this third problem, it's a little bit more complicated, but I think with a little thinking through it, we can get it. And if you were able to get it without me explaining it, then that's awesome and you are headed in the right direction. So, what should we do here? Well, we have a y term on the right side, and we have a k term on the, we also, also on the right side, we have a k term. Now, this k term might throw us off a little because, well, it's not exactly a variable and it's not exactly, I don't know, it's not y, it's not x, it's just k. It's weird, you know? So what should we do with it? Well, in cases like these, I like to leave the arbitrary letter that's not related to either of the variables on the side where there is no variable that's going to be integrated. So I would divide both sides by y to isolate the k and y from each other. So it would become 1 over y dy, and I'd multiply both sides by dx. So it equals negative k dx. Now from here, we can just integrate because the k is really just a constant. It's like a c. It's not a variable, so it could be any number. So when we integrate this, it's going to be pretty simple. So when we integrate 1 over y, well, we know from calculus that the integral of 1 over y would be the natural log of the absolute value of y. And we know that a constant, the integral of a constant is just that constant times x. So on the right side, we would have negative kx. And of course, because this isn't a problem with any initial value or particular condition they want us to satisfy, we would add a plus c here. Now, the problem is looking a little funky right now. We can't just leave it like this. So something I like to do, and something you should always do, is you should raise both sides. You should write e on both sides and raise it to that term. So the natural log of y, if we take if we exponentiate both sides, sorry, that was the word I was looking for earlier, but we know that e to the natural log of y, for my logarithmic rules, that's just going to end up being the absolute value of y. And e, the right side would be e to the negative kx plus c. So when you do this, of course, this simplifies to just being the absolute value of y. And this becomes e to the negative kx plus c. Now, this also looks a little complicated, but luckily for us, there's a way we can simplify it. So we know that the absolute value, we know that e is a constant. And what's the rule about exponentials? Well, we know that, for example, if I had e to the 2 plus 3, this can be rewritten as e to the 2 times e to the 3. That's just a rule we know about exponentials, that when you're adding them up here, it's the same as just multiplying them. So this can be rewritten as the absolute value of y is equal to e to the negative kx times e to the c. Now we know e is a constant and c is also a constant. So we can use that trick I showed you guys in the problem number 2 and write that c1 is equal to e to the c. Now, another thing that I would really like to do before this to make it even simpler, because I kind of want to get rid of this absolute value term over here, is knowing that when you have an absolute value, you're really just saying that y is equal to plus or minus this whole thing right here, because it could be positive or it could be negative. We don't know because it's an absolute value. And we gotta respect all the signs that we've put. So y equals plus or minus, sorry, that's a bad plus sign. Let's make that a little cleaner. But we have y equals plus or minus e to the negative kx times e to the c. Now, in our trick here where we wrote c1 equals e to the c, we can actually write that c1 equals plus or minus e to the c. Because at the end of the day, it's just a constant, you know? We don't really care if it's positive or negative, as long as we're representing it as the fact that it is a constant. So we can get a much more simplified answer that y is equal to c1, which we wrote is plus or minus e to the c, times e to the negative kx. And there we arrive at a much simpler answer than what we had thought we would have gotten when we were up here with all this natural log mess and exponential mess and being confused by the k. And yeah, we really arrive at a simple answer that represents our work well. One last thing I want to mention before we wrap up the introduction video is that the problem number 3, the practice problem we just solved, is almost an exact example of a real-world application that is very important in many scientific and engineering fields. It's the concept of exponential growth and decay. Now, this idea of exponential growth and decay is usually modeled by the differential equation dp over dt is equal to kp, where p is the population of something, or let's say it's the population of a town that we're modeling the growth of, or the amount of bacteria in a petri dish that's growing over time. P is the population of what we're tracking. And when we say dp over dt equals kp, k is just some constant value that is saying that the rate of change is directly proportional to the population. So what does that mean? We're basically just saying that if we have a population, the rate of change of that population is going to depend on itself. So the rate of change when the population is large, it might be very different from the rate of change of the population when the population is small. And that's all going to depend on what that constant k value is. But that's just a very cool application, and I'm really glad that we were able to cover it in the intro video. And I think that this was plenty to think about, and there's lots more to explore with differential equations. So it's going to be a very exciting journey, and I'm very happy to be able to help you guys. So if you want any more practice problems on the differential equations we practiced in this video or initial value problems, please let me know in the comments, because I'm always willing and happy to upload more videos to help you guys study and learn. Until next time, thank you for watching.